Sounds me, sorry. Okay, well, let's get started. Welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson, the director, and it's been a great week at Green Bank. We're open for business again. The cafeteria is full. We have students, summer students on campus. We have visitors on campus. So and the weather has turned beautiful. So there's a nice feel in the air that we're back into business and open for business again. So it's nice to see all the people. If you want to visit, please do. The disposition letters went out for your semester 22B proposals. So you should have been informed. If you haven't been informed, please let me know. But everyone should have heard by now, and check your email if you haven't checked. All right, so without any further ado, I'll hand it over to Dave, who can introduce today's speaker.
Thanks, Jim. My name's Dave Frere. I'm a scientist here. We're happy to have Kim Emig here to talk to us today about low-frequency radio recombination lines. She received her PhD from Leiden and is now a Jansky Fellow, a postdoctoral fellow in NRAO Charlottesville. So we can go ahead and take it away, Kim, and share your screen. I do want to mention, if you have questions, we can take it at the end of the talk. Just put them in the Q&A box. So thank you.
Okay, thanks, Dave, and thanks, Jim. So yeah, I'm Kim Emig, and I'm a Jansky Fellow at the NRAO in Charlottesville. And today I'm going to talk to you about the Cygnus X star-forming region. So you can see this image here, the red filter showing the 1.4 gigahertz radio continuum. You can see this supernova remnant here. Hopefully you can see my mouse, my cursor when I'm moving it around. And so this here is a supernova remnant, but the rest of the radio emission that we see is actually coming from ionized gas. In green, that's showing the UV heated PAHs in 8 micron, and in blue, that's showing the cold molecular gases traced by 13CO. And so today I'm actually going to focus on the diffuse interstellar medium in the region and how we can probe that using low frequency radio recombination lines. And this work is done together with this great group of collaborators here. And so I'm going to focus on this 30 square degree survey that we've done using the GBT at 340 and 800 megahertz. And so you can see the footprint of the survey on the left. And so I'm going to introduce you to the Cygnus X region, what we know about diffuse ionized gas, and then just show you the first results using this data. And ultimately, we're interested to know how the stars and the interstellar medium are intimately connected in the galaxy's life cycle. And particularly, these massive stars have a profound impact through the energy and momentum that they inject into the medium, through their photoionizing radiation and the photoionized gas, through their radiation pressure, and through the stellar winds and supernovae. So in particular, for this survey, we're looking at the diffuse ionized gas and the cold neutral medium. So we'd like to know how this photoionized gas affects the evolution of the ISM in the region and thus future star formation. And the cold neutral medium, this is a cold component of atomic gas and the more diffuse molecular gas that CO doesn't necessarily trace. And we want to know how the molecular clouds are forming and being destroyed at what rates, and how the physical conditions of this gas changes in the presence of these massive stars that have formed. So in order to do this, we're going to try to address this by determining the temperature, density, and size of these gas phases using the recombination lines and how their intensity changes across frequency. And we want to relate the characteristics of this gas and its morphology to other phases of the ISM, like the kinematics and the turbulence injected by supernovae, stellar winds, and ionized evaporated flows. And then with these sort of pressures that we're able to estimate from the temperature and the density, we can compare that with sort of pressures that from other phases of the ISM and other feedback mechanisms. So two other reasons that we're interested in these observations are one, these observations turned out to be sort of a pilot survey for this GBT diffuse ionized gas survey at low frequencies, which is surveying 78 square degrees of the inner galaxy using the same observing setup. And then we're also making the first detections of recombination lines outside of the local universe. So for example, you can see on the right here, this hydrogen recombination emission at a redshift of 0.89. And so it's really useful to have these detailed studies in the galaxy and understand these tracers better so that we can interpret these higher redshift observations. Okay, so when we look at these multi-wavelength images of the Milky Way, the Cygnus X region stands out in a number of these tracers. And so although we're looking down a spiral arm in this direction, it's most of the emission coming from this that we see in this direction is coming from this sort of co-spatial region of star formation at a distance of 1.5 kiloparsecs. And so here again, I'm showing an RGB image, this time using mid-infrared filters, where we have the 3.6 micron in blue showing primarily stars, the 8 micron again showing the UV heated pHs, and the 24 micron showing the warm dust, which is really well correlated with ionized gas emission. And we see some regions where we have stars actively being formed, and they're still embedded in this in these dense clouds. There's somewhat more evolved regions that have formed recently, but they're starting to disperse that denser material, and the ionized gases are sort of able to leak out into the surrounding medium. And so there's all of this active star formation, but there's still a large reservoir of molecular gas, so more than 10 to the 6 solar masses that's available there to form new stars. And there's also this SIGOB2 association, which is having a profound impact on the medium. So this has it's an association with a stellar mass of about 10 to the 4 solar masses, and this age between 3 and 5 million years. And so when like supernovae, we expect them to start going off at around 3 million years. So it's kind of curious that we don't see the supernova here. But for the individual stars of SIGOB2, which you can see the OB stars in green here, at this stage, they're individually not surrounded. They're in H2 regions, but they've really cleared away that material. And we can see some of these other features showing the profound impact of the stellar winds from SIGOB2. So it's been known for a long time that the radio emission that we see in this region is largely coming from ionized gas. And so, for example, we recently looked at this region with a pointing of LOFAR at 150 megahertz. And you can see how that is really similar to what we're seeing at 1.4 gigahertz. And this is consistent with thermal emission from ionized gas that starts to become optically thick at 150 megahertz. And so we can assume something about the geometry and estimate the density, and this has a median value of around 40 particles per centimeter cube, and it's most likely fully ionized. And we think the majority of the emission that we're seeing is coming from these ionized regions, which are sort of flowing out into a lower density environment. But for some of the ionized gas emission that's sort of closer to CGOB2, that could be more related to the stellar winds. So we can also look at, we can also identify the ionized gas using radio recombination lines from hydrogen. And so this at higher frequencies is this really great spatial resolution. Here we're showing the integrated intensity, the integrated emission of the spectrum at each pixel. And we can see those, the features that are synchrotron dominated, like the supernova remnant and some of these background galaxies, they don't show up in this ionized gas emission, but instead those sort of compact H2 regions, which are, they're nice and bright in this recombination line emission. And because these are also spectral line tracers, they're spectral lines, they can give us really useful information about the kinematics in the region. And so how the gas is flowing, maybe in or sort of being pushed out through some feedback mechanisms. So as a quick introduction to radio recombination lines then, so these are the transitions that we observe when you have an electron recombining with an atom, and it does so at high principal quantum numbers. And then the electron just transitions between one energy level, so from an energy level of 100 to 99. And so this is a really low energy transition that we observe at radio wavelengths, and from 1 gigahertz or 100 gigahertz down to 10 megahertz, there's more than 800 of these lines per each element. And so at the higher frequencies, the recombination lines are brightest from hydrogen, and particularly in really dense ionized gas. So this is typically H2, sort of compact H2 regions. As we go towards lower frequencies, that the recombination line emission from those H2 regions sort of drops off, and we have this low density gas that dominates the emission. And actually, for low density gas, the emission can be amplified and stimulated, so it becomes much brighter at these lower frequencies. And then lastly, at the lowest frequencies, carbon becomes the most prominent emitter and traces those cold diffuse clouds from the CM. And so here, again, introducing the GBT observations, you can see the spatial resolution, the frequency coverage, the number of recombination lines and their principal quantum number. But these observations that we've made really build upon existing recombination line surveys that we did at 150 megahertz with LOFAR. So you can see the outline on the right in there, or the coverage on the right in blue. Also the recombination lines from the EBIS survey, which covered 3 recombination lines. You can see the current footprint that we have is in red. And then of course at high frequency, we have the data from the GBT diffuse ionized gas survey, which gives us that nice spatial resolution, and is also a good sort of anchor point where we don't expect the line intensities to really be amplified that much. They're really in LTE. And yeah, so this is through this survey, they're also covering the inner galaxy and some other well-known star-forming regions like Cygnus. And what we ultimately want to do, we have this really nice frequency coverage across these 5 different bands. And we want to measure how the line intensity is changing as a function of frequency. Because for different physical conditions like the temperature and density, we expect different behavior, different changes in the line intensity. So you can see some models on the right here, and how just minor differences in the temperature can result in big differences in the line intensities, particularly like in the LOFAR band here. or I guess another general point is that as we're going towards higher frequencies, these are generally going to probe the more dense gas phases. They're going to peak at higher frequencies. Okay, so now showing some results. These are spectra, which are spatially integrated just across the whole region. And a big thanks to Pedro Salas, who's been doing the data reduction. This is just preliminary. It's not quite the final version, but in a really good state already. And so this, in these spectra at these 3 different frequencies, you can we can see hydrogen is the brightest line there, and it spans plus or minus 30 kilometers per second, and it's actually brightest at 800 megahertz. So this is already indicating something about the characteristic densities of the gas in this region. We see carbon. So these recombination lines are offset from hydrogen by 150 kilometers per second. So these spectra are actually shown with respect to hydrogen. But yeah, these lines have narrower line widths because this is a colder gas, but we also see that it's spanning a narrower range in velocities. And we can see that we don't see much emission at 6 gigahertz, but as we go towards lower frequencies, this emission is getting brighter. There's also helium, which we can see really clearly detected with this higher signal to noise ratio data at 800 megahertz. And so it's really helpful that Riley Owens has been looking at the data cubes and fitting the line components and decomposing these different components in a spatially resolved way in the data cube. So he's a summer student working with Lauren, and is going to be doing that this summer. And so here we're looking now at moment maps across these 3 different frequencies and how the emission is spatially distributed. And you can see the different resolutions of the frequencies here. So we can see this general agreement when we look at the emission at these different frequencies. But if we look a little bit closer, we can see that the emission from these compact H2 regions no longer is so bright at 800 megahertz. So it's starting to drop off there. And particularly when we look at 340 megahertz, you can see that sort of the peak in intensity is shifting a bit spatially. And so we can see that also here close to the supernova remnant. And so the next steps then are, we really want to do that, look at the line intensities as a function of frequency at each in a spatially resolved way. And for carbon, I'm showing the moment zero maps of carbon, but again, this image with CO, so you can sort of compare against that. And yeah, so the carbon lines that are going to peak at that are brighter at 800 megahertz are tracing gas that's more dense. So we can see some peaks in emission here towards some of these brighter star forming or young star forming regions that that changes a bit as we're going to these lower frequencies. So we want to compare this data with observations of CO or H1 absorption, that we have some really good maps in this region. And so lastly, I'll just highlight or sort of demonstrate some of the work that we can do. So with work led by Anish Raushi towards the supernova remnant DR4 or gamma Cygni, with single pointings, also towards DR21, a well-known star-forming region. We looked at the emission at these 3 different frequencies, and we can compare that emission with sort of the H1 profile that we're seeing here, and this H1 absorption feature, which is like easier to distinguish in the data cubes, and we can and also the CO in green. And so we see that these the velocity of this carbon, this gas traced by the carbon recombination lines agrees well with these other sort of cold gas tracers. And we can also discern some information from the line widths of the recombination lines. So yeah, I actually should have mentioned that you know, we see these lines in emission at the higher frequencies, but we see that it goes into absorption at 150 megahertz. And so that agrees, you know, that's predicted by the models, but for really high density gas. So it's really like unusually, it's a pretty high frequency that this is going into absorption. So that's already indicating dense gas. But we can also get additional constraints from the line widths. And so we, at these lower frequencies, the line can be radiation broadened or pressure broadened, or collision, yeah, also. And this is going to tell us something about the radiation field and the gas density. So within this information, we constrain the density of this cold neutral medium phase to sort of these values here, which are quite high, higher than what we're seeing in other regions. And so we think that this gas might actually be shocked, might be tracing a shocked layer. So the next steps then would be to use these densities and conditions to estimate formation and destruction rates of the molecular gas. Okay, so that's all I had time to share with you today. So in conclusion, this Cygnus X is a dynamic environment surrounding this massive stellar association. There's also young regions of recent and embedded star formation, and we're really just starting to scrape the surface of this GBT data. I also told you about low frequency recombination lines and how they can provide key constraints on the gas temperature, density, and size through their line broadening and also variations in the line intensity. And these GBT surveys like GDIGS and GDIGS low are exploring the diffuse ISM in unprecedented capacities. So thanks a lot for your attention, and I'd be happy to take any questions.
Thank you very much, Kim, for a lovely talk. Go ahead, people. Excuse me, put your questions in the Q&A box if you have any. As we're waiting for them to come in, I'll just ask a question. I was sort of surprised that density was like 10 to the 4th and the electron fraction was pretty small in comparison. So these are a lot of hydrogen, but very little amount of ionized material within them. So I just found that interesting. I mean, was that surprising, at least the density you were saying?
Yeah, so because we think this is really a neutral phase, we think that the carbon, it's only carbon that is ionized and hydrogen isn't. So it's really just, we actually estimate the neutral hydrogen density by assuming, by taking the abundance of carbon, which is sort of 10 to the -4.
Okay, so you're assuming a carbon abundance. Yeah. Okay, thank you.
May I take prerogative and ask a question?
Sure, Jim.
So how do you, so the normal explanation for carbon is it's photodissociated, right? So you have to expose gas to an ultraviolet radiation field, but that gas is usually quite warm. How do you reconcile having cold temperatures and ionized carbon in the same place?
Yeah, so these, this is tracing a layer that, yeah, you can't ionize hydrogen, but you can still ionize carbon. So it has that 11.3 EV ionization potential. But and yeah, so this would be ionized by far UV photons. Yeah, trying to think what else I could say.
Yeah, the PBR model suggests that the physical temperature of the gas in these regions is 100 Kelvin to 300 Kelvin if it's any sort of substantial UV.
Oh yeah, right. Yeah, but that's
This is
really like
colder.
in a PBR environment, right? But you can have more diffuse phases where you're not in the presence of really extreme UV fields from stars, but something that's more diffuse and further away. So yeah, some actually like some of the gas like that's traced at the 800 megahertz could be more the PDR environment, but the gas that it's going to peak at the carbon gas is going to peak at the lower frequencies is going to be a bit more diffuse and further away from the stars.
Great, thanks.
We had a question that came in. It's a very general question, and they're asking, where does the ionization energy come from?
Yeah, so this is coming from stars, mostly starlight. So we have, there's some regions like we were just talking about that can be really close to those recently formed stars. But yeah, you can also have for gas that's maybe further away from the COB2 association, you can get, I guess, a lower flux. Yeah.
Thank you. Oops. Somebody provided a link to a paper in the Q&A. Which people can go to. We have quite a few participants here. Does anybody else have a question? Oh, we have a hand up. Do we have a hand up?
There's also a question in the chat.
Oh, I missed that. Okay.
Yeah, so can deuterium be observed? I mean, we're not that I know people have detected it. I know some people have looked for this signature and haven't found it. But yeah, it would be interesting to do more investigation to that.
Just to follow up, if you could detect deuterium, can you literally just get the abundances pretty much straight up?
Yeah, that would be amazing.
That would be
to be able. Yeah, but I think that would be really amazing if you could do that. But it's just it hasn't been done yet. But really useful.
Let's see. I'm going through the chat. Okay. Does anybody else have any follow-up questions? Oh, and this is coming in on the chat too. There's another question that came in. How good is the assumption that the radiation at different frequencies are coming from the same places, i.e. some regions being smaller than the beam and differences in optical depths?
Yeah, I think that's a very fair question. And yeah, definitely something that we first need to investigate in the data to sort of look at the velocities of the different components and see if they're really tracing the same gas or not at these different frequencies. Yeah, we hope that they are, and we hope that we can separate out different components by looking at how their emission is changing as a function of frequency. But yeah, we do see structure. So we can do this analysis at something like 10 arc-minute resolution or lower. But that's true that we do see even structure at higher resolution. So yeah,
Let's see here. And I think I don't have any.
Yeah, I guess maybe I should also address like the optical depth. So these are, we don't really, optical depths won't, optical depth of the recombination line emission, it's always really optically thin. So optical depths of sort of 10 to the -3 or 10 to the -4. So we don't, that won't be an issue.
I think I'm having a hard time getting them. Oh, my Q&A box got moved. I'm sorry. We had a couple other questions. On the two plots, and I'm going to just read it off. On the two plots you have on the conclusion slide, the carbon and hydrogen emission are spatially separated. Are there any infrared signatures looking at the PDR emission that can help you predict where carbon will be bright?
Yeah, so if we look at the far infrared, for example, we see sort of cold dust, which we think is can be tracing a really similar gas phase. Where did that question go?
Oh, wait,
And
in the answer box. Sorry.
yeah, and so but yeah, I guess so. It's this gas phase is also notoriously hard to try to isolate, because it's hard to observe just the cold component of atomic hydrogen, and then and it's hard to observe the diffuse gas, which isn't traced by even like 12CO, the main tracer of the molecular gas. So so yeah, the first things that we need to do are really compare with these just H1 absorption features that we see, compare it with the CO, compare it with the dust continuum that's tracing the colder dust there, and yeah, hopefully we can sort of correlate those things for the carbon gas that we're tracing. And I guess regarding the carbon and the hydrogen emission, yeah, so if the carbon emission is tracing those really young star forming regions, right, like maybe the denser regions of the layers of the photodissociation regions, then we can expect a closer agreement sort of spatially with the two tracers. But if we're tracing this really more diffuse phase of the gas, then actually we might not expect to see some agreement between this largely ionized gas, or we could see really clearly separated components between the ionized gas and then this more neutral phase.
Okay, that sort of answers the question on do carbon and hydrogen recombination lines show similar kinematics? You were talking in spatially there. There's an
yeah, so they do. Yeah, so they are. So I guess in terms of the we see more extreme velocities in the hydrogen and the ionized gas, and with the carbon gas, is tracing more of like the systemic kind of velocities of the region. So we do see differences.
And that's because the carbon's the denser material.
Mm-hmm.
Okay. Okay, I think we've answered all of our questions. So thank you very much, Kim, for an excellent talk. We have their next community Zoom will be Adam Hinks from the University of Toronto on June 8th, mapping the gas and intercluster filaments with the SC effect. So thank you, everybody, for attending.
Yeah, thanks, Dave.
Okay, bye. And then we'll let Paul, you can do your